Good evening, everybody. Professor Ayorinde welcoming all of you to another session of Organic Chemistry's review. In today's session, we are going to review for your final examination for the spring 2015 semester, which is scheduled for Wednesday, April 29. So today's session will be the first review session. Then on Monday, April 27 at 7 p.m., we are going to have another review session. So you have a complete review for your final exam. Okay, so since most of you are in Dr. BAKARE's class, I am going to use a previous final exam from Dr. BAKARE for today's review session. Okay, I noticed some of you are already here, Ayana, Victoria, Zeni, so you are all welcome. Okay, now let us, we are going to, I do hope that all of you have a copy of that final exam with you, because we are going to start right away. So let us go to problem 7. Okay, Ayana, can you go ahead and read the, this question for us? Hello?
I'm having a hard time seeing the instructions. Oh, here we go. Suggest structures for the compounds E to J in the sequence of reactions shown below.
Okay, thank you. Okay, this question 7 says suggest structures for the compounds A to J in the sequence of reactions shown below. Of course, as you guys already know, this is a set of questions in which you need to know what the reagents do. So to get this started, let me ask you a couple of questions. Now, we are supposed to start with this molecule here. Does anybody know what class of compound is this? Can you tell me what class of compound is the starting material? Okay, pick up the mic or send me your response through the chat window. Okay, ketone, excellent, very good. So you are giving a ketone, and then also you are giving sodium borohydride followed by hydronium ion as a reagent to react with the ketone. Does anybody have an idea what does the sodium borohydride followed by hydronium ion, what will it do to a ketone? What will it do to a ketone? Okay, form alcohol, excellent. Okay, very good. In other words, anytime you have a ketone and you have sodium borohydride followed by hydronium ion, what you get is sodium borohydride will convert the ketone to a secondary alcohol. That is very, very good. So what do we have as a product? It is here. Okay, so we are going to get that secondary alcohol. Okay, now that is A. That is A. Now they also tell us to take the secondary alcohol, in other words, compound A, and react with phosphorus oxychloride, of course, in pyridine as a solvent. Okay, now does anybody have an idea what does this phosphorus oxychloride do with a secondary alcohol? What does it do with a secondary alcohol? Okay, going to form alkene. So this is a dehydration reaction. Excellent. Keep in mind, folks, we are starting with the simplest question in this exam, which is essentially requiring that you know what those reagents do. Okay, so you do say that we are going to form an alkene. So essentially, therefore, anytime you have a secondary alcohol or a tertiary alcohol, and you react with phosphorus oxychloride, you get dehydration, and so the you are going to form an alkene. Of course, dehydration means that you are losing a molecule of water. Very good. Okay, they also told us, to take compound A and react compound A with phosphorus tribromide. Okay, what does phosphorus tribromide do to a secondary alcohol? That reagent, what does it do to a secondary alcohol? Anybody has an idea? What does it do to a secondary alcohol? Let's see here. Okay, it will replace the hydroxy group with, exactly, very good. It will replace the hydroxy group with a bromine atom. Okay, so in this case, compound B will be this here. So here we are forming an alkyl bromide, that is compound B. Okay, now let us move on. Now they also now tell us to take compound B and react compound B with, you have magnesium here. Okay, to react compound B with magnesium. What do you think the magnesium will do? Okay, excellent. That is Zeni. Zeni said we are going to form a Grignard reagent. Very good. So the magnesium in ether as solvent will react with an alkyl bromide to form a Grignard reagent. Essentially, this type of molecule here. So we say this is a Grignard reagent. However, what they've done here, after you have formed the Grignard reagent, they also now tell you to now take the Grignard reagent and react with a formaldehyde, which is this molecule here. To react with formaldehyde, okay, then you follow that up with hydronium ion. Okay, what do you think you are going to get when you react a Grignard reagent with formaldehyde? What do you think you are going to get when you react a Grignard reagent with formaldehyde? Okay, of course, yes, that will give you a primary alcohol. That will give you a primary alcohol. Now, on the other hand, if you have your regular aldehyde reacting with a Grignard reagent, in that case you get a secondary alcohol. So in this case, when our Grignard reacts with the formaldehyde, we are going to get this product here. We are going to get this product here, which will be a primary alcohol. Okay, keep in mind here that this carbon here, this carbon right here, that is this carbon of the formaldehyde. Okay, in other words, anytime you take your Grignard reagent, in this case, the Grignard reagent will be this here. Let me change the color of my pen. Our Grignard reagent is this. Okay, so you react this Grignard reagent with this formaldehyde, and then you follow that up with addition of hydronium ion, and that will give you this product here, which is compound C. I see already joining us already. You are also welcome. Okay, so that is the product after this series of reaction right here. Okay. Okay, so let us move on. Take this out of here. Okay, keep in mind, Grignard reagent will react with formaldehyde to give you a primary alcohol. Keep that in mind, a primary alcohol. Okay. Okay. So now they now tell us to take compound C. Take compound C, which is this molecule here, and react compound C with PCC in methylene chloride as solvent. Okay, what do you think PCC will do with a primary alcohol? What does PCC do to a primary alcohol? Anybody has an idea? PCC reacting with a primary alcohol. Let's see, what does that give us? An aldehyde. Excellent, excellent. So I think you guys are getting ready for your exam, because once you know your reagents and once you know what those reagents do, I guarantee you Can you guys hear me? If you can hear me, give me a happy face. Okay, good. I think my mic just went off for a brief second there. Okay. Now, if you take PCC and you react PCC with a primary alcohol, of course, just as Ariana has told us, we get an aldehyde. We get an aldehyde, okay? And that is compound D right here. Okay, now, they now want to take compound D, which is our aldehyde, and react with silver oxide in the presence of ammonium hydroxide. What do you think you are going to get? What does silver oxide do to an aldehyde? What does silver oxide do to an aldehyde? In this case, in the presence of ammonium hydroxide. Carboxylic acid, excellent. You get the carboxylic acid. Folks, keep note here, this question here is basically mostly memorization, which means that you need to know what those reagents do. Okay, so let us see what is going to be the product here. This will be the product for this. Technically, this is the product you are supposed to get. You actually get the conjugate base of an aldehyde, because you are dealing with, because what you have here, this is a basic condition. For you to actually get the carboxylic acid, what you need to actually have here is to have this as step 1, and then step 2, you add hydronium ion. Okay, in that case, you will actually now get your carboxylic acid. So let me take this out. If that is the case, then you get your carboxylic acid. But if you wrote carboxylic acid for this particular problem, I think nobody is going to mark you wrong for that answer. So anyway, silver oxide will oxidize an aldehyde to the carboxylate salt, the salt or the conjugate base of the carboxylic acid, and upon acidification, then you get your carboxylic acid. Okay, so let us move on to the next set of questions to see here. Okay, now they want us to take compound D. Let me take all of this out of here. so as not to confuse everybody. Take this out. This out. Now they want us to take compound D, which is an aldehyde, this here, and then react with a Grignard reagent here, okay, followed by hydronium ion. So in this case, we are starting with an aldehyde, and we are reacting with a Grignard reagent. So what type of product are you going to get here? We know that we are going to get an alcohol. Is it going to be a secondary alcohol or a primary alcohol? Okay, reacting this Grignard with an aldehyde. Okay, let us see what the product will be. What is that going to be? Let's see here. Okay, that will give you a secondary alcohol. Excellent, excellent. That will give you a secondary alcohol. So therefore, we are going to have this here. So we have our aldehyde. Secondary alcohol. Then this Grignard right here, let us use a different color for that Grignard. We say that Grignard is this here. Okay, don't forget that in this particular reagent here, this Grignard here, this C5H5, that is your benzene ring, and that is what I have right here. And of course, the this here, this CH2 right here, okay, and that is that right here. Okay. Okay. No, let us see here. I'm sorry about that. I've got too many CH2s here. Let me take one of them out. Sorry about that. So that will be this here. Okay. So this CH2 right here, and that is this CH2 right here. Okay. So what we have here, what have we done? We're reacting a Grignard reagent with an aldehyde, we get a secondary alcohol. Now keep in mind, in the last problem that we had with Grignard, we reacted Grignard with formaldehyde. Formaldehyde is the simplest aldehyde, which has two hydrogen atoms attached to carbonyl. Formaldehyde is this here. And the reason why we get the primary alcohol with formaldehyde is because this carbonyl here has attached to it two hydrogen atoms. However, if you have your regular aldehyde, you will get a secondary alcohol, which is what we have in this product right here. Okay? So keep that in mind. Okay, now take all of this out of here. Okay, there is nothing here, so forget about this. Okay, then we got one more reaction in this problem before we leave this alone. Now they want us to take the secondary alcohol, compound F. They want us to take compound F. Take all of this out. Take compound F, which is this here, which is a secondary alcohol. Now they want us to react with PCC again. What class of compound do you think we are going to get? In other words, they want us to react the PCC with a secondary alcohol. Okay, excellent. We are going to get a ketone. Very good. So we are going to get a ketone. Let's move this a little up. So we do have some more here. We are going to get a ketone, so therefore let us look at the ketone. So we have this here. Okay? So the secondary alcohol is oxidized to a ketone, and that is compound G. Keep in mind, once again, I keep reminding you, in this set of questions, all you need to know is to know what those reagents do. So you really do need to know what all of your reagents do. Once you do that, you will find that organic chemistry is fairly simple. Now, they now want us to take compound G, which is a ketone, and react with a primary amine. Take all of this out. React with a primary amine, which is this here. Okay, anytime you take a primary amine and you react with a ketone, we are going to get what is called an imine. In other words, we are going to replace the carbon-oxygen double bond with a carbon-nitrogen double bond. Okay, so therefore, what is the product that will be here? Okay, so we get that product, which is called an imine. That is an imine, and therefore, keep in mind the reaction of a primary amine, which is what this molecule is, with a ketone or an aldehyde will give you an imine, and imines are those compounds in which you have a nitrogen-carbon double bond. Okay? Okay, and finally, on this set of problems, we have this here, supposed to react this ketone here with this reagent. Okay, does anybody know? Let me take all of this out. Does anybody know what is the name of this reagent here? What would you call this reagent right here? Anybody has an idea? Anybody has an idea? What would you call that reagent? Okay, Victoria is joining us again. You are welcome. Oh, Wittig reagent. Excellent. That is all right. Thank you. That is a Wittig reagent. So what does the Wittig reagent do with the carbonyl of a ketone or the carbonyl of an aldehyde? What does it do? What does it do? The Wittig reagent, what does it do with the carbonyl of a ketone or the carbonyl of an aldehyde? Okay, it's fairly simple. Of course, it replaces the carbon-oxygen double bond with a carbon-carbon double bond. Keep that in mind. The Wittig reagent replaces the carbon-oxygen double bond with a carbon-carbon double bond, okay? Okay, so the product here will be this here. This case will be CH is here. And of course, you have this here. Okay, if you notice here, let me take this out of here for better clarity. You notice here, this carbon here of the Wittig reagent right here, that is this carbon here. Okay, so what have we done? We have simply used that to replace the oxygen of the carbon-oxygen double bond. And of course, you can see here, the methyl here is this methyl right here, okay? Okay, so the point to be made here is anytime you see a carbonyl of a ketone or the carbonyl of an aldehyde, and you see a Wittig reagent, what you do is to replace the carbonyl, that is the carbon-oxygen double bond, with a carbon-carbon double bond using the Wittig reagent. The carbon that is attached to the phosphorus will be the one that will replace the oxygen. This is phosphorus right here. Okay. Okay, now, if you understand what we just did with this problem number 7, give me a happy face. Okay. Okay, so now let us go to problem 13. Okay. Now, if your mic is working, I do not know how many of you's mic is working. Can you pick up the mic and read question 13 for us? Okay. Okay. Yeah, apparently, most of you do not have working mic. Ayana, can you go ahead and read question 13 for us? Okay, maybe Ayana must be having problem with her mic also. Okay. Okay, well, yeah, go ahead. Zeni, go ahead.
Give the major products formed in the following reactions.
Can you read that again, Zeni? I did not hear you. You need to
Hello?
raise your voice. I could not hear you.
Give the major products formed in the following reactions.
Okay. Well, Zeni, I noticed that your mic was on, but I did not hear your voice. Anyway, let me go ahead and read this question here. The question says, give the major products formed in the following reactions. Okay. This is another case of knowing your reagents. Okay, so let us look at the first one here. A. Okay, in A you have a nitride. Keep in mind you have a nitride, which is this molecule here. You have a carbon-nitrogen triple bond. Anytime you have a carbon-nitrogen triple bond, and of course you have a lithium aluminum hydride, what happens is that this carbon here is reduced to a methylene group, becomes a CH2 group. Okay, and then the nitrogen here, you add 2 hydrogen atoms to the nitrogen, so you get a primary amine. So what is the product going to be here? Let us see here. Take this out of the way. So here we are going to get this product here. 1, 2, 3, 4, 5, 6. Okay, and of course, see what we've done here. If I number this carbon here, let us go ahead and number this carbon here. If we say the carbon that is attached to the nitrogen is 1, that is 2, that is 3, that is 4, 5, 6, 7. Let's call this 8 here. Okay, so what we have, this is carbon number 1. Keep in mind that that becomes a CH2 group, the carbon that is attached to nitrogen, and that is 2 right here, 3, 4, 5, 6, and that is 7, and that is 8. So the point to be made here is anytime you have a nitride, and you have this reagent here, which is lithium aluminum hydride followed by hydronium ion, you get a primary amine, and the carbon of the nitride becomes, in this case, becomes a methylene group of a CH2 group. It's a methylene group. Which is a CH2 group, okay? Okay, so let us go to the next one. Okay, that is B. B. For B, what we have here, can anybody tell me what class of compound is this? Is B. What class of compound is this? What type of functional group do you have there? Epoxide. Excellent. You have an epoxide. Now, when you have an epoxide, and you are giving acid, in this case hydrogen chloride, you are going to open up the epoxide. Now, the product you obtain depends on the nature of the epoxide. In this case, we have an epoxide in which you have, if you take a look at this carbon here, let us say this carbon here, this is a tertiary carbon, okay? And here, this is a secondary carbon, okay? Anytime you have an epoxide with a tertiary carbon, and you have acid, you have hydrogen chloride or hydrogen bromide or hydrogen iodide to react with the epoxide, what you are going to get is the opening of the epoxide such that the halogen will attack the more substituted carbon. In this case, the halogen will attack this. Let me number this here. Just say this is carbon 1 here and this is carbon 2. Okay, the halogen will attack carbon 1 because it is more substituted. This reaction will be taking place as though it is what we call an SN1 reaction. Okay, so therefore it is going to be an SN1 type reaction, in which case we form a carbocation, and that is why we are going to get this product. Get that. It's here, of course. Okay, see what we get here. We open up the epoxide. The hydrogen, if you look at what is happening here, this hydrogen here attaches itself to the oxygen, and that is why you get this right here. And of course, the chloride, which is this here, attaches itself to carbon number 1. And that is why you see the chloride attaching to this carbon here. Okay, and that is because the epoxide, you're starting off with an epoxide that has a tertiary carbon. In that case, you are going to get what we call an SN1 type substitution reaction. Okay, let us go to C. Okay, with C, we also have here, we have an ether. Keep in mind, an epoxide is also an ether, which is what we did in problem B. So now in C, we have an ether, which is a carbon and oxygen attached to 2 carbon atoms. And what we have here, we have hydrogen iodide to react with that. Okay. Now this is another case in which the hydrogen, take all of this out of here. This hydrogen here, the first thing it will do is to attach itself to the oxygen, and once it attaches itself to the oxygen, and therefore it then gives you a good leaving group, just as in the case of the epoxide. And what do you get? This hydrogen here, let me go ahead and put that in there. Let's say this hydrogen is attached to here. And what you get a protonated oxygen atom there. And therefore, because in this particular instance, the 2 carbon atoms that are attached to oxygen, one of them is a primary carbon, which is this here, and the other is a secondary carbon, which is this here. Now, so what you are going to get, you are going to get an SN2 reaction, which is to say that the iodide which is to say that the iodide, this iodide here, this iodide right here, will come here and attack this carbon here, and then open this up. Okay, so you are going to get an SN2 reaction. So what do you get as the product? You get this product here. Okay, you get that product, plus you also going to get another product from this part of the molecule right here. From this part of the molecule right here, which will be, in this case, will be a secondary alcohol, plus you are going to get this. And that is why they have this here, plus. Okay, so you are going to get this. Okay, so those are the two products you are going to get. Now keep in mind, anytime you have an ether or an epoxide and you are giving hydrogen chloride or hydrogen iodide or hydrogen bromide, the first thing that happens is the hydrogen will attach itself to the oxygen, thereby making the oxygen, the alkoxide group, a good living group. Once it becomes a good living group, then you could either get an SN2 reaction or an SN1 reaction. In this particular case of compound of this here, we are going to get an SN2 reaction because, keep in mind, SN2 reaction takes place when you have a good living group attached to a primary carbon atom. And that is what we have in this case. So the two products here will be this here and this right here. A secondary alcohol, and that secondary alcohol is coming from, take all of this out of here, and that secondary alcohol is coming from this part of the molecule right here. Okay, and the ethyl iodide, which is this here, is coming from this part of the molecule after the iodide displaces the oxygen atom. Okay. It attacks the list. Very good. Okay. Very good, Ayana. That's what you said. Very good. Now let us do D. Let's go to D. Let's see here. Let us move this up. Okay. Okay. In order for clarity, let me take all of this out. I hope that you guys have already, if you are taking down any notes, that you've already written this down. Take this out. Okay, for D, in the D, what do they have here? Actually, there was an error here. I talked with Dr. BAKARE about this. There is supposed to be here, something is missing here. This is catalytic amount of sulfuric acid or acid. Supposed to be here. Okay. In this case, you have a catalytic amount of acid, and you have 2 moles of an alcohol. In this case, ethyl alcohol. What you are going to get here, keep in mind, anytime you have an alcohol or an epoxide or an ether, and you have acid, the first thing that is going to happen is the protonation. The first thing that will happen is the protonation of the oxygen atom, thereby making the hydroxy group a good living group in this particular instance. And once that happens, then another molecule of the alcohol will attack with this carbon here. Let us number this carbon here. Let us say this is carbon 1 and carbon 2. Once you protonate the oxygen atom, then that hydroxy becomes a good living group. Then another molecule of the alcohol will simply come and attack carbon number 1 Okay, using the oxygen as in this case as a nucleophile. So you will get this here. So the product here will be this. Okay, so you are going to get an ether. Okay, so just a case of let me go ahead and explain this a little further for you. Okay, what do you have first? You have okay, so you have the alcohol, and then you have the acid as a catalyst. The first thing that happens is that the non-bonding pair of electron on the hydroxy group attacks the proton, so you are going to get this. And once you get that, then what happens here, the next molecule, another molecule of the alcohol, it will just say they use a different color here, will now simply come here using the pair of non-bonding electron on oxygen, attack this carbon here, and then displaces this here, and that is why you end up getting this product right here. Okay? Okay, so let us do the E, and then we are finished with our problem 13. Take this out of here. Okay, for E, what do we have for E? We have a carbon-carbon double bond, and so for E we have a carbon-carbon double bond, and then we have this reagent, chlorine in the presence of water, chlorine water. Okay, what do you think is going to happen here? A carbon-carbon double bond and chlorine water, chlorine and water. Chlorohydrin, excellent, excellent. You are going to get a chlorohydrin. Chlorohydrin is when you have a hydroxy group and chlorine atom attached to adjacent carbon atoms. In other words, carbon atoms that are next to each other. So what would that be? It would be this here. Okay, the stereochemistry here, of course, is a trans stereochemistry. Okay, so you are going to get that. That is the product, and that is what we refer to as a chlorohydrin. Now, once you take the chlorohydrin, now you react the chlorohydrin with hydroxide. This hydroxide here, which is coming from here, sodium hydroxide. Once you react the chlorohydrin with an hydroxide or any base, what is going to happen? The hydroxide is going to come here and pull off the hydrogen atom from the hydroxy group. So in essence, you are going to get this here. Let me see. You don't have to write the mechanism, but I just want to explain this to you so you know exactly how that happens. Okay, so you get that. Okay, once you get that, keep in mind these are trans to each other. You now have an alkoxide. So this alkoxide now, what does it do? It simply comes here. This oxygen here will now come and displace the chlorine in an SN2 type reaction, and the chlorine will leave. And then what you end up as your product, you end up with an epoxide. Okay, so that is how you do that. So in this case, the hydroxide simply comes here, remove the hydrogen from the hydroxy group, this hydroxy group, and then once it does that, you form an alkoxide. The alkoxide will now react as, in this case, as a nucleophile to displace the chlorine atom, just as I've shown you in this molecule here. And so your final product will be an epoxide. Okay, so let me take this out of the way. So folks, what you've seen here is essentially knowing what your reagent do. Once you know what your reagent do, you find that you will not have any problem with organic chemistry. And in this particular instance here, once you have a chlorohydrin and then you have an hydroxide in the form of sodium hydroxide or potassium hydroxide, then the product you are going to get will be an epoxide. Okay? Okay, so let us go to problem. What problem is that? 13. Let's go to 18. Okay. Okay, if your mic is working, can you go ahead and pick up the mic and read question 18 for us? So Chelsea, you are welcome. I notice you are trying to type something. Okay, what are the question you are asking? Can someone please tell me all the problems you've done? Oh, okay, I see. Oh, okay. Anyways, let us do 18. Okay, somebody pick up the mic and read question 18 for us. Okay, go ahead, Ayana.
Give the major organic product of each of the following reactions if none is predicted. Write in R.
I can't hear you.
Give the major organic products of each of the following reactions. If none is predicted, write in R.
Ayana, can you pick up the mic again? I noticed your mic was on, but I did not hear you.
Can you hear me? Can anyone hear me?
Okay, folks, let me, I cannot hear. That is the second time I cannot hear anybody. Okay. Give me 1 second here. Let me see if I can do something here. Let me check something out because this is the second time somebody has been speaking to me, but I could not hear. Just give me 1 minute, okay? Let me check something out. Okay, Ayana, pick up the mic again and see if I can hear you.
Hello?
Okay.
Can you hear me?
Okay, well, I cannot. Okay. Okay, so let me go ahead and... now, if you can hear me, give me a happy face. If you can hear me, give me a happy... Okay, very good. So all, you guys can hear me. Okay, let me go ahead and read this question here. Okay, question 18 says, give the major organic products of each of the following reactions. If none is predicted, write NR. Okay. Okay, what do we have here? Let us start with A. In A, we have an alkyl benzene, which is this molecule here. We have an alkyl benzene, and we have this reagent here, potassium permanganate in dilute acid. What kind of product do you expect to get? What kind of product do you expect to get? Alkyl benzene and potassium permanganate. Benzoic acid, excellent, very good. Benzoic acid, very good. So we get this. Okay, folks, anytime you have anytime you have an alkyl benzene, it does not matter what kind of alkyl group you have on the benzene. That alkyl group, even if it is this long, that alkyl group will be oxidized completely to a carboxyl group. In other words, you are going to get this here. No matter how long the alkyl group is, you will get. Notice what we have here. You are going to lose all of the carbon atom in the alkyl group except the carbon that is attached to the benzene ring, and that carbon now becomes your carboxyl group right here. Okay. Now, however, if the carbon that is attached to the benzene ring does not have an hydrogen, there will be no reaction. For example, if I gave you this, here, okay, and I'll say what will be the reaction here? Potassium permanganate in dilute acid. Because this carbon here that is attached to the benzene ring does not have an hydrogen here, what you are going to have to write here is no reaction. There will be no reaction. In other words, for that reaction to take place, the carbon that is attached to benzene must have an hydrogen atom. Okay? Now, supposing I give you this. Let me take all of this out. Supposing I give you this here, what product do you think you are going to get here using potassium permanganate with dilute acid? What are you going to get? What do you think you are going to get? 2-benzoic acid. Excellent. Very good. Okay, each one of those carbons that is attached to benzene, each one of these carbons here, this here, and this here will become carboxyl group. Okay, and you lose the rest of the molecule. Okay, so therefore, in this case, the product will be this here.
I hope you're not talking in my thing. In my sign. Hey, we're up into the.
Okay, if that is clear, give me a happy face.
You're talking what you doing? Look on that.
Okay, very good. Okay. Let us go to the next one. Let me erase this. Okay, now let us do B. Okay. Oh, no. Before we do B, let's finish A. Sorry about that. Let's finish A. Okay, as a continuation of A, they want us to react the benzoic acid, this here, with bromine in the presence of iron 3 bromide. Okay, what do you think we are going to get here? What will be the product here? What is going to happen? Let's go ahead and write this. Okay, metabromo, exactly. Metabromobenzoic acid. Excellent. Okay, metabromobenzoic acid. Let us go ahead and write. Okay, this is here. Let us put our carboxyl group right here. Okay, metabromobenzoic acid. Very good. In other words, the carboxyl group is a meta director, which is to say that any incoming group is directed to the meta position of the molecule. Okay, very good. Okay, now let us go to B. Let us go to B. In B, we have benzene reacting with nitric acid in the presence of sulfuric acid. Okay, what do you think we are going to get here? What kind of reaction is this? Okay, that is sulfonation. Exactly. We are going to introduce, nitration. Thank you. We are going to introduce a nitro group to the benzene ring. This reagent here, nitric acid in the presence of sulfuric acid, what it does is to replace an hydrogen on the benzene ring with a nitro group. Okay. Let's go ahead and put this here. So we get nitrobenzene. Okay, good. Now, they now told us to now take the nitrobenzene and now react with tin chloride in the presence of dilute acid. What do you think we are going to get? What does that do to a nitro group? Okay, form aniline, and in other words, the tin chloride will reduce an NO2, the nitro group, to an amino group. Excellent. So in this case, we are going to get aniline. Okay, very good. Folks, you see how easy this is. Once you know those reagents and what they do, these problems are fairly easy. Okay, so what we have here, this reagent here, what it does is to transform a nitro group to an amino group. This is your amino group right here, the NH2 group. Okay, in this case we get aniline. Okay, now let us move on. Let us go to C. In C, we have ethyl benzene, and then we have MBS, M-bromosuccinimide, in the presence of a peroxide. This is a peroxide right here, and of course the carbon tetrachloride, that is your solvent. That is just acting as a solvent. So what do you think that will do? Okay, there's a question here. I think a recent chapter, but oh, okay. Okay, oh, okay, all right, thank you. Bromine on the secondary carbon. Very good. Bromine, so Ore has given us the answer to that. In other words, what Ore has told us is that this reagent here, this reagent right here, what it does is to replace one hydrogen, the hydrogen on this carbon here, one of the hydrogen on this carbon here, which we refer to as a benzylic hydrogen, because that benzylic. Benzylic hydrogen, we are going to replace one of the benzylic hydrogen with a bromine atom. That is what this reagent will do. Therefore, the product will be this here. Okay, so that is what that will do. That is what the MBS in the presence of a peroxide will do. Will replace one of the benzylic hydrogen with a bromine atom. Now, they now want us to take the secondary alkyl bromide, which is this here. They want us to take this and react with potassium hydroxide. What do you think the product will be? What do you think the product will be? Okay, all of these are simply just knowing your reagent. What do you think the product will be? Okay, okay, good. This will be yes, vinylic benzene. Excellent. So this will be dehydrohalogenation. In other words, we are going to form an alkene by removing a bromine atom and an hydrogen atom. So you get a vinyl benzene. Who said that? That's Chelsea. Very good. Very good. Okay, so we get this here. Okay, and that is what that reagent will do. Potassium hydroxide will remove bromine and hydrogen, form a molecule to form an alkene, and that is what we refer to as dehydrohalogenation. Okay, let us move on. Okay, the last question here, which is okay, we are supposed to react this compound here, which is the nitroanisole or M-nitroanisole. Okay, with chlorine in the presence of iron 3 chloride. What will be the product? Okay, now let me go ahead and number this. I want to ask a question here. Let's call this carbon 1. Let us call this carbon 2, carbon 3, 4, 5, and 6. Okay. Okay, you guys said we are going to get chlorination. Okay. Where do you expect the chlorine to be? What, which carbon will the chlorine go to? Okay, 6 and 2. 6 and 4. Excellent. It will be 6 and 4. 6 and 4. It will not go to 2 because of steric hindrance. So you are going to get 2 products here. You get 2 products. You get this here. Okay, go to carbon 4. You're also going to get, because this molecule, the direction of this reaction will be detected by the methoxy group, because the methoxy group is it will be the director here. It is an auto para director, so it will direct to the auto and the para position. The para position is position number 4, and the auto position, in this case, it does have 2 auto positions, but because one of them is sterically hindered, it will go to, let us have this here, you have this here, have this here. It will go to this right here. Okay, notice there will be no chlorine in the 2 positions because of steric hindrance. Steric hindrance. Okay. Okay, now we have finished this question. If is there any question on this before we go to the next one? Okay, let us go to 20. I think we're moving right along. Let us go to 20. Okay, let's try this mic business again. Zeni, can you pick up the mic? I noticed that your mic was, I believe, was on or so. Can you pick up the mic and see whether I can hear it? And read question 24. Okay, maybe about or if your mic is working. Okay. I think we might be having problem. Okay, let me go ahead and read question 20 for everybody. Okay, question 20 says, outline a reaction scheme to show how you will prepare 1-bromo, 2-chloro, 4-propobenzene from benzene and any appropriate organic compounds. Says include all reagents and show structures of all intermediates in each step. Okay. So this is a synthetic problem, which means that all of those reagents we have been using in the previous questions, now we're now going to begin to use them. This is the time where you now have to begin to think critically. So now critical thinking is very important here. Okay, so what do we need to do? Let us write the structures of what they want us to do. They told us to start from benzene and make this compound here. Okay, so we have benzene. And we're supposed to make that 1 bromo, 2 chloro, 4 propobenzene. Okay, so let us have this here. 1, 2, 3, 4. Okay, bromo and chloro. Okay, so they want us to make the benzene, starting from benzene, to make this compound right here. Okay, now, does anybody know what is the first step we are going to take here? Now, let's do a little bit of analysis. If you look at the product they want us to make, you notice here the relationship between the chlorine atom and the, oh, is it supposed to be propyl? 1, 2, 3, 4, I'm sorry, that's supposed to be propyl. Okay, the relation between the chlorine atom and the propyl group right here is a meta relationship. In other words, a 1-3 relationship between them. And we know that chlorine is an autopara director, and then the propyl group is also an autopara director. So the question now is, how do we do this in order for us to be able to direct the chlorine or the propyl group meta to each other? So what that will tell you is that you have to introduce some group that is a meta director first before you do anything else. Okay, so I've been giving you that information. Okay, Chelsea said we start with bromination. Okay, you want to do bromination? Okay, if you do bromination, let us do that. Let's follow what Chelsea said. Okay, so we want to start with bromination. Okay, so bromination. Okay, so you get this here. So you get your bromine, right? Okay, now what do you do after that? Okay, I'm following your lead here. Okay, Chelsea, no, continue. That is good. Then what do you do now? Well, you're on the right path. Go ahead. Then do acylation of the ring. Okay, very good. Then you want us to do Friedel-Crafts acylation. Very good. Now you want us to take the bromobenzene and do Friedel-Crafts, right? Very good. So far, so good. So your Friedel-Crafts that you want to do, oh, you want to use the appropriate Friedel-Crafts. Let me use bond line structure here. Okay, so you want to use okay, so you want to use the appropriate acyl chloride. Keep in mind you need 3 carbon atom in the benzene, so that is why I am using this acid. Okay, using this acid chloride here. Now, so that will give us, so where do you, the bromine is an autopara director. Okay, right, okay, so very good. I see where you want to take us here. Very good. So far, this is, I am following what Chelsea is giving us here. So now you have this in para position. Okay, now Chelsea says, then reduce the, reduce the carbonyl. Okay, what reagent are we going to use to reduce the carbonyl? What reagent are we going to use to reduce the carbonyl? Okay. Okay. Now, this so far I am following what Chelsea is giving us. I just want to. I'm not saying this is correct, but let us see. You want us to use well, we could do hydrogenation. Okay, very good. So let me take this. We could reduce that, right? We reduce that, and then we get, we use hydrogen in the presence of palladium. Okay, and so that will give us no. No, if I do not reduce it, okay, I see. You say I should not reduce it. Okay, very good. So you change your mind. You don't want us to reduce it. So you want me to do what? To now do the, let us see here. Let's see. Let me take my eraser. Okay. Okay, so what do you want me to do now? Do chlorination now? Yeah, okay, good. So now you want us to do chlorination. Let us see. Okay, I'm glad you changed your mind because that will have taken us nowhere. So now, at this point, the bromine is an auto-para director, so it will direct to the auto position. Fortunately for us also, the AC group, this group here, the acyl group, what we call acyl group, is a meta director. So therefore, whereas the bromine will direct auto, so that simply just works fine, and therefore you get this. Give myself some space here. Okay, so now what do we do at this point? Now what do we do now? Now reduce. Okay, now reduce. Okay, good. Now we reduce. Now you can now do your hydrogen in the presence of palladium. Okay, very good. So you notice what we've done here. You have to take account of all. Let me put everything in focus for all of you, so you can see the whole sequence. Okay. So what have we done? We started with bromination. Okay. Keep in mind, each one of these reactions, you know them individually. So this is where the critical thinking now comes in. Okay. Okay, so the first one, bromine, we do bromination on benzene to obtain bromobenzene. And then after that, we did the Friedrich-Krafft acylation. The Friedrich-Krafft acylation to now obtain this product here. And then knowing that we need to introduce the chlorine in the meta position and also to the bromine, and that is why we follow that sequence. And then we did the chlorination, in which we use chlorine in the presence of iron 3 chloride, and we obtain this product right here. And finally, we reduce the carbonyl, the ketone, to the CH2 group to now obtain our final product. We did the reduction with hydrogen in the presence of palladium to obtain the final product. Okay. Okay. So that is what we've done here. Keep in mind what are the only way you get a chance to do this is for you to know those individual reactions. So let me take all of this out so that it does not. Okay. Okay, so we finished this particular problem here. Okay, now let us go to problem 15. There is no question on that. Okay, let us go to 15. Okay, now I'm still trying to see if this mic will work. Ayala, can you try to talk again and see? Something is happening. I don't know what that is. Read question 15
the main
first.
organic product formed in each of the following reactions. Show stereochemistry of the product where necessary.
Okay, okay, well. Yeah, I see your mic was on, but I couldn't hear you. I could not hear you. Okay. Let's see here. Okay, well, let me go ahead and read question 15 for everybody. Question 15 says, give the main organic product formed in each of the following reactions. Show stereochemistry of the product where necessary. Okay, very good. Now, what we have here, does anybody know what type of reactions are these? Anybody has an idea what type of reactions are these? Okay, dienophile reaction. No, this is a Diels-Alder reaction. This is what we call Diels-Alder reaction. It's a Diels-Alder cycloaddition reaction. Okay, now what does that say? Anytime you have a Diels-Alder cycloaddition reaction, generally you have a conjugated diene, which involves a conjugated diene. For Diels-Alder, you need a conjugated diene. And then you then need also a conjugated diene, which generally will have a molecule in which you have alternating carbon double bond. In other words, here you have a carbon-carbon double bond right here, a carbon-carbon double bond right here, separated by a carbon-carbon single bond right here. Okay, this is a carbon-carbon single bond. So that is what we call a conjugated diene. So for Diels-Alder to work, you need that conjugated diene system. But also, more importantly, the conformation of the diene system must be what we call, it must be in the cis, what we call cis conformation. Now, what does that mean, cis conformation? What that means is that the double bond, those two double bonds must be on the same side of the single bond. Okay? That means those double bonds must be on the same side of the single bond. Notice that the two double bonds are on this side of the double bond, of the single bond. On the other hand, if you have this, if I have this here, supposing I have this is what I call trans conformation, because you notice here, this is the trans conformation. For you to be able to do a Diels-Alder reaction, the molecule must be in the cis conformation. Okay? Okay, so keep that in mind, the cis conformation. So having given you that, let us now take a look at this. So you need, so this is our diene, which is a conjugated double bond system. And then you then need a carbon-carbon double bond, a single carbon-carbon double bond, okay? Because you need the pi electron there to react with the conjugated diene, and that we call the dienophile. So this carbon-carbon double bond here, this here, we call it a dienophile. So for you to have a Diels-Alder reaction, you need a diene, which is a conjugated double bond system in the cis conformation. Then you need a dienophile, okay? Once you have those combinations, let me take this out. Okay, this is what you should do. What I want you to do, go ahead and number the carbon of the conjugated system. Only the carbons that are involved in the conjugated system as 1, 2, 3, 4. So I'll say this carbon is 4, this is 2, this is 3, this is 4, okay? Then the 2 carbon of the dienophile, I will call them, this is 5, and this is 6. So what happens, in the Diels-Alder reaction, you end up forming a cyclic cis-member ring in which carbon 1 is attached to carbon 6, and carbon 4 will be attached to carbon 5. So keep that in mind. That is what you get. So therefore, what will be the product? And then once you do that, the 3 double bonds will disappear, and only 1 double bond will be left, and the double bond that will be left will now be between carbon 2 and 3 right here. Okay? So what do we have? All Diels-Alder reaction must form a 6-member ring. Okay? And we say this is, let me go ahead and number the carbon. These are carbon 1, carbon 2, carbon 3, carbon 4. We say these are carbon 5, these are carbon 6. All the time you must have a 6-member ring. And then we say that the only double bond that is left, because you are going to use 3 double bonds in this reaction, the only double bond that is left will now be between carbon 2 and 3 right here. And once you do that, the rest of the molecule then go ahead and write them where they belong. In this case, you have the carboxyl group is on carbon 6, so we need to go ahead and include that. So it's still here. Okay, and of course, all you have on carbon 5 is just the hydrogen that was there before. And that will be the product. That will be the product. Okay, do you follow that? If you follow that, give me a happy face. Okay, now let us do B. Let us do B. Let us go ahead and do B. Okay, B is a little bit more complex. Let us go ahead and do B. Now, if you follow what I told you before, what are you going to get? I will get this. Go ahead and number the carbon, the carbon that are involved in the conjugated system as 1, 2, 3, 4. So we say this is 1, this is 2, 3, 4. Okay. Then the carbon of the dienophile, we say this is 5, and this is 6. Okay. Then go ahead and number the rest of the carbon if they are in there. Okay, you have a carbon attached to 1. I will say that is well, the one attached to 4 I will call this 7, and the one attached to 1 I will call this 8. Now let us now go ahead and put together the product of this reaction. Okay. Keep in mind you must form a 6-member ring. Okay. So let us look at our 6-member ring. That is our 6-member ring. Okay. So now let us go ahead and number that. This is carbon 1, carbon 2, carbon 3, carbon 4, Okay. Now, this is carbon 5 right here, and this is carbon 6 right here. And now, keep in mind we are only using 3 double bonds in this reaction. So, the double bond will now be between 2 and 3. Also, now remember, in the dienophile, this dienophile, we only use one of the double bonds. So therefore, there is a double bond that is left here between 5 and 6. Somebody has a question for me. You do not get 2 double bonds. Oh, okay. Now, okay, so let us look at the rest of the molecule. Now, on carbon 5, we have, attached to carbon 5, we have this ester here. Okay, so let us go ahead and put that in on carbon 5. We have an ester there right here. On carbon 6, all you have is hydrogen. So, now, what is missing? Can anybody tell me, based on the numbering that we did, what is missing? What is missing? 7 and 8. Excellent. So now, we now say we have carbon 7 and 8 missing. We know that carbon 7 is attached to 4, and carbon 8 is attached to 1. So now we simply going to go ahead and do that. Okay, so now this will be our carbon 7 here, and this is our carbon 8. So you are forming a bicyclic molecule. So you are forming a bicyclic compound, okay? And that will be the product. Now, if you want, you could write this product here using a 3-dimensional structure. But if you don't want to do that, you could leave it the way it is. It is written right here in a 2-dimensional form. But if you want to write it in a 3-dimensional form, then it looks like this. Okay. Okay, so now we have, okay, this here, this here. Of course, hydrogen is here. Okay, now let us go ahead and number those carbons. I see your question. You're trying to ask me a question, Chelsea. I'll be right with you. Okay, so this is our carbon 1, carbon 2, carbon 3, carbon 4. This is our carbon 5. This is our carbon 6. And this is our carbon 7. And this is our carbon 8. So now, if you do not want to write it in a 3-dimensional form, as I've written here, you could simply just keep it as it is right here. Okay, if you want to play safe and just leave it right here, that is fine. Okay, but the point here is, Diels-Alder reaction always give you a 6-member ring. And then what you need to do, once you form your original 6-member ring, then attach all of the other carbons to the appropriate position in that 6-membered ring system. Okay, does somebody have a question? Wouldn't you also get a bicyclic compound if the dienophile was? Oh, of course, yes, of course. Let me see here. The question you are trying to ask here, supposing you have this, you want to increase the complexity of this. Supposing we have this, let's go to this here. Supposing I say, give me this here. Right? And this here. Okay, so what will be the product here? Okay, of course the product will be, okay, this being our, let's do our numbering system, 1, 2, 3, 4, okay, this is our 5, and this is our 6, okay, and I say this is our 7, and this is our 8, okay. The rest of everything is still attached to 5 and 6. So what is going to be the product? The product will be this. Draw your initial 6-member ring. Okay, the double bond is now going to be here. Okay, and then you are going to then between 5 and 6. Let's go ahead and number this. These are 1, 2, 3, 4, 5, 6. Between 5 and 6, you still have this. Okay, that is still there. And then, of course, you have the bridge at 7 and 8. You have the bridge at 7 and 8, which is this here. Okay. Now, if you want to now write this in a 3-dimensional form, I will simply just do this. Now I will now have this here. This is a double bond here. Okay. Then I will have this here. Now in this case, the hydrogen here will be coming at you on top. The stereochemistry here, you have to show the stereochemistry here. The hydrogen now will be, this is a case, okay. The hydrogen will be going on top. In other words, the hydrogen now will be in this position in the same direction as the bridge system. Okay, and then this group here will be going away from the bridge system. So this group, this bridge, notice this bridge as really should have this as going away. Let me properly indicate that and take this out. Okay, so that bridge will be going away. I'll say okay, and that is what you get. So somebody asked me, supposing you have a ring system in the dienophile, which is what we have here. In that case, you simply did what you did before, and then go ahead and indicate the rest of the molecule, just as we did before. Okay. So here you get this here. This is the 2-dimensional form of the product. But if you want to write it in the 3-dimensional form, this is what it will look like. Okay. I think we are almost running out. Oh, we have spent more than 1.5 hours. Let's see here. What problem is that? I believe that was problem 15, I think. Yes. Okay, let's see if we can do 2 more and then we get out of here. Let's go to 3. Okay, 3. Okay. Let me read this for you guys because I think we're having problem with your mic. Number 3 says, propose a synthesis of dimethyl starting from p-methoxypropionol as the only source of carbon. Okay. In other words, they want us to make this complex molecule here starting with only this as the source of carbon atom. Okay, very simple. Let us take a look at this. Let us do some analysis here. Now, if you look at the product, take a look at the product, you will see that in the product, this part of the molecule in the product look very much like this part in the starting material. Okay, the same thing on this side. So it does look to me that we are joining, what we are doing is joining the starting material from the position of the carbonyl, the carbon oxygen double bond. So the question I have for you is this. how do you make a carbon-carbon double bond from a carbonyl? How do you transform a carbonyl, that is a carbon-oxygen double bond, to a carbon-carbon double bond? There is a reaction for that. Yeah, we did it before, but yeah, by the way, I think we did this before in one of those previous online session. So anyway, does anybody have an idea? We wouldn't spend too much time on this. Yes, make a Wittig, exactly. Make a Wittig. In other words, you simply start to make a Wittig here. Very good. Once you understand that you need to make a Wittig, okay, so we simply go ahead and make. For you to make a Wittig, you need the alkyl bromide. So that means you need to transform the carbonyl to an alcohol first. So you could use sodium borohydride, step 1 and step 2, or you could use lithium aluminum hydride. If you do that, then you get your alcohol. And then once you get your alcohol, what reagent do we need to transform the alcohol to a bromide? Okay. Okay, phosphorus tribromide. Okay, very good. Keep in mind, you need to know those reagents. Okay, I read your question. Yeah, I think we will do one before we go, Ayana. Okay, so now you get this. And then once you do that, and then what you do at this point, you now make a Wittig out of that. To make your Wittig, you use it triphenylphosphine. Use triphenylphosphine to make your Wittig. Oh, too big. Okay, so you use triphenylphosphine, say step 1, and then step 2, use butyllithium. Butyllithium. Okay, let me move this a little. Okay, so triphenylphosphine and butyllithium, that will give you your Wittig, which is right here. Okay, so we have this here. So that means we are going to have Wittig right here. Okay, this is your, and then your, keep in mind your Wittig you have. Okay, and so this is what your yelid. So you make your yelid. This is what we call a yelid. This is your Wittig reagent. Now your Wittig reagent now, simply now take it and react with this here. Let us call the starting material. Okay. Now react with the starting material, which is the other starting material. Okay, and that is how you get that, okay? So what have we done here? Let me go ahead and bring everything into focus. Okay, so we started with, by reducing, we make our Wittig by reducing the ketone with the sodium borohydride. We get the secondary alcohol. Then we transform the secondary alcohol to a secondary alkyl bromide. using phosphorus tribromide, and then we use the phosphorus triphenylphosphine followed by butyllithium to make our Wittig. And so these are Wittig right here. And then you react the Wittig with another mole of the ketone, and you get your final product. Keep in mind, the Wittig reagent will react with a carbon-oxygen double bond to give you a carbon-carbon double bond. And that's what we have here. So let us go to, that was 3. Let's do 5. Let's see. Somebody's outlining a reaction showing the, okay. Yeah, somebody wants us to do an aldo. Let me see here. Well, let us do this 5 here. Maybe I don't see an aldo in this problem set. Does anybody know where the aldo is in the problem set? Give me the number. Maybe we can do that. If you know where it is on the problem set, just send me the number. Anyway, let's try to do 5. This here says, okay, this problem 5 says outline a reaction scheme to show how you will achieve the following transformation employing Grignard reaction. Okay? Okay, so this will be fairly simple. You need to use a Grignard reaction here. Now let us analyze the products and see what we need to do. If you take a look at this product here, okay, does anybody know how many carbon atoms do we have in this product? Anybody has an idea? Oh, okay, I got you. You say 21, good. Anybody has an idea what, how many carbon atoms is in this? Okay, you said, 13. Okay, very good. Okay, so we have 13 carbon atoms here, right? How many carbon atoms in the starting material? 9. Okay, good. So that means we need to form a new carbon-carbon bond with the Grignard. They told us we need to use a Grignard, okay, in order to form this. Okay, another question that I have for you is this. We want to make a secondary alcohol, right? Okay, we are going to react Grignard with a molecule to get a secondary alcohol. What type of molecule do we need to react with a Grignard with to get a secondary alcohol? An aldehyde. Okay, great. So now we got all of the elements that we need. The only thing that is missing now is that we have this carbonyl here. You cannot make a Grignard. In other words, we want to make a Grignard with this starting material, but you cannot make a Grignard when you have a ketone in the molecule. So what do we need to do? What do we need to do? Anybody has an idea? What do we need to do? Protect the ketone, exactly. Very good. We need to protect the ketone. So the first thing we are going to do is to protect the ketone by using a ketal. Okay, so we are going to use ethylene glycol. By the way, ethylene glycol, that is the same molecule that you use as your antifreeze for your car. Antifreeze fluid for your radiator in your car. Anyway, so we are going to use ethylene glycol to react with that. So therefore, we are going to get this. Let us go ahead and say we have this here. I hope I get my carbon number right. So we have that. And then we are going to form the ketal. Let me use this here. Take this out so it does not get too long. Okay, so we form the ketal. The beauty of the ketal is once you form it, you could now make your Grignard reagent. And once you make your Grignard reagent, you perform your Grignard reaction. The moment you add dilute acid, the keter will go back to a ketone. So therefore, at this point, let us now make our Grignard reagent. To form a Grignard, everybody knows how to do that. Okay, ether. And then I'll say step 1. And since you guys already told us step 2, we are now going to form, because you told us we need to use an aldehyde. So we are going to use an aldehyde that has 4 carbon atoms right here. Okay, so let us go ahead and put that in. So we say we use this here. Okay, let me move this up a little bit. Okay, now, so I say that is step 2. I then say step 3. Okay, then I add dilute acid to that. Once we do that, that gives us the desired product. Okay, let me take this out of the way. Okay, now what have we done at this point? The moment you add the dilute acid right here, okay, you open up the epoxide, the keter. The keter goes back to the ketone. That's what we have here. Okay, if you follow that, give me a happy face. Okay, very good. Okay, good. Okay, somebody said 8. Let's do 8. 8 is very simple question, so let us do that real quick. And then we go to, somebody said 21 as an aldo. So we could do that, and then we go. 8. Okay, question 8. This should be very simple. We shouldn't take too much time on this. This says, circle the ring on which chlorination of N-methyl N-phenylbenzamide below this compound here is expected to occur. In other words, this reaction here on this molecule, okay, where would the chlorination go? Let me go ahead and label the ring system so that you guys can help me here. Let us call this ring A, and let us call this ring B. Okay, we all know that this reagent here, what it does is to do chlorination on the benzene ring. In other words, we replace an hydrogen on the benzene ring with a chlorine atom. So this is the question I have for you. Where would the chlorine go? Which ring would the chlorine go? B. Okay, very good. That is correct. Why would it go to B instead of A? Okay, because the nitrogen is attached to the molecule ring B, which contains electron. The nitrogen contains non-bonding pair of electron. Okay, which is an activating agent. In other words, because the nitrogen contains okay, can you guys hear me? I think I lost my internet for a minute. Okay, I lost my internet for a minute. Well, that's technology. Okay. So, what happens here? Okay, you guys have B, which is correct. It is B because the nitrogen is attached to ring B, which is an activator. So that is an activator. Whereas on ring A, the carbonyl is attached to ring A, which is a deactivator. So therefore, the product will be this here. So that's a very simple one to do. And the nitrogen will be an auto-para director, so it could come in the chlorine could go in the auto position. We could also get another product that goes in the para position. Okay, so we are going to get two products here, and the other one will be this here. Okay, so that is that. So we finished 8. Now let me, so somebody say we definitely need to do an aldo. Okay, so there is a question here. Will we have to write both auto? Yeah, I would advise that you write both of them. Okay. Somebody is asking, do we need to write both of the products? Yes, go ahead and write both of the products. You have nothing to lose. Okay, somebody said we need to do an aldo, and that is question number 21. Let us see if we can do that before we leave. I was really planning to do that on Monday, since we are coming back on Monday. Do you want us to do it on Monday, yes or no? Because we all spend no more. Okay, so at that point, let us just call it a day for today, because we have spent almost 2 hours now, and I do not want this to be too long. It will be difficult to process if it gets too long. So I will remind you of the session on Monday. I will send you a reminder email by Monday afternoon. But keep in mind that we are going to have a session on Monday at 7 p.m. In the meantime, I will post the recording of this session in my YouTube page by tomorrow afternoon. So enjoy the rest of your evening, and I will see you on Monday. For those of you who want to stay around for another 5-10 minutes, I will stay around for another 5-10 minutes once you stop the recording.